Hello everyone, welcome to Memoneet. I am Aprajita, your chemistry SME. I hope all of you are doing good. And how is the preparation for BPT4 going on, students? I hope you have watched the previous video lectures and you are preparing well for BPT4 because there are two important chapters that are coming in this Bhramastra part test 4. Both chapters are important from class 11th. Okay, they are basic chapters as well as they carry a high weightage in your NEET examination. That's why we are covering them right now. Okay, so in the previous two lectures, firstly we talked about the introduction part, how the subatomic particles got discovered. We studied Thomson's model, Rutherford's model, and in the last lecture I told you what were the developments that led to the Bohr's atomic model. Then we discussed the Bohr's model for the hydrogen atom and its limitations as well. Okay, so today we are going to focus on the quantum mechanical model of the atom. So what we are studying is the quantum mechanical model of the atom because Bohr's model also had certain limitations, so that were again overcome by the quantum mechanical model, right? So that's what we are going to cover in our today's session, and that will be our last topic of this chapter. But this topic is the most important one. Okay, so you have to study it very carefully because this is the most important topic from this chapter. You get a lot of statement based questions, correct incorrect type questions based on this topic. All right, so that's what we are going to study today. And yes, I'll again tell you, if you are having any issues or any doubts, please ask us in the comment box. Okay, we will definitely try to resolve your issues and queries. So whatever you are feeling, whatever is lagging, or if you feel that something is missing, so you can definitely comment in the comment box. Okay, and whatever questions we are giving you, try to solve them. All right, students, please join the Telegram channel. In the Telegram channel, let me tell you, we are giving you daily targets. So sometimes what happens is we ourselves are not able to plan our day or plan what we are going to do, how to study and everything. So we have got your back here. We are giving you daily targets along with the Brahmastra part test, like how to approach for the test, what are the things that you have to do. Okay, and yes, in the evening we have daily quizzes, not for chemistry only but for biology and for physics also. We will be posting daily quizzes and targets in the Telegram channel. So if you people want to join that Telegram channel, please go through the description. There you will find the link. Okay, and you can join that if you want to study in a well planned manner. Okay, so yes, we will be starting with our today's session, quantum mechanical model. Now this quantum mechanical model was not just randomly, like it did not came up randomly. So let me tell you a little bit about it. When the Bohr's model came up, there were certain limitations regarding that, right? It could not tell us about the chemical bonding, right? That thing, it did not tell us. It did not tell us. It explained the spectra of hydrogen but could not explain the splitting of the lines, the Zeeman effect, Stark effect, and it could not explain the spectra of multi-electronic systems. Okay, for one electron system like hydrogen, helium ion, lithium ion, it could do, but for multi-electronic system it could not explain, right? So again, there were certain developments. There were certain developments that led to the quantum mechanical model of the atom, and those two developments were dual nature of matter, okay, and the Heisenberg's uncertainty principle. So you might have heard of these terms also. See, in the last lecture only we discussed the dual nature of radiation. Okay, so in this session we will see the dual nature of matter as was suggested by D. Broglie and then Heisenberg's uncertainty principle, which led to the discovery of your quantum mechanical model because Bohr's model could not explain these things. So let us first start, students, with our dual nature of matter. Okay. So students, these two things that I told you, that is the dual behavior of matter as well as the Heisenberg's uncertainty principle, it led to the formulation of your quantum mechanical model of the atom. So this French physicist de Broglie, he actually proposed that just like the radiations, just like the electromagnetic radiations, they exhibit your dual behavior. Matter also exists dual behavior, means matter also exhibit the particle like and wave like properties. Like, so just like we have photons now, which are the small packets of energy, right, of light. So photons have momentum as well as wavelength. Momentum means they show particle like nature, and wavelength means they show wave like nature. So de Broglie suggested that electrons should also have momentum as well as wavelength. Okay, and he actually said that every particle, or be it a macroscopic or a microscopic particle, has a wavelength associated with it. Okay, so here from this analogy he gave this relationship, so we just need to know the relationship, don't go into the derivation part. Okay, so this is important here. So actually the de Broglie wavelength is given by lambda. So lambda is your it is called de Broglie wavelength. Okay, so it is actually the wavelength associated with the matter particles. All right, so it is given by h upon m v. Okay, so here we can say h upon p, where p is the momentum, m is the mass of the particle, v is the velocity of the particle. All right, and so m into v, it gives you the momentum. All right, and I hope you know what is h, right? We have discussed it in the last class. It's Planck's constant, whose value is 6.626 into 10 to the power minus 34 joule second. Okay, so that is h, and p is the momentum. So de Broglie wavelength is given by h upon p. All right, so actually, you know, I am telling you that wavelength is associated with every matter particle, but what happens is for macroscopic particles, like let's say I have a ball with me, so the mass is too much that the wavelength come out to be very less, and we cannot just see it, right? Or we can, it can go unnoticed because the value of wavelength come out to be very less. But for microscopic particle, we cannot neglect it because their masses are very less. So the wavelength is considerable in that case. So we need to consider the wave-like property of the electrons also. And it actually got you can say that his prediction actually was proven to be true when, like, it was confirmed experimentally when it was found out that the electron beam, they undergo diffraction. And you know that diffraction is the phenomena which is shown by waves, right? Diffraction. So when electron beams undergo diffraction, it was proved. So it was actually confirmed what de Broglie said, that yes, matter or electrons also have the wave-like as well as particle-like properties. And this thing, electron beam diffraction, right? This is also used in your electron microscope, which uses actually the wave nature of the electrons. Okay, so that was confirmed. The another very important idea that led to the development of quantum mechanical model was the Heisenberg's uncertainty principle. Now actually Heisenberg actually stated that it is actually impossible to determine simultaneously the exact position and exact momentum of an electron. Okay, momentum means if we cannot uh, determine simultaneously the exact position or exact momentum of the electron. Now the it can be explained mathematically as delta x into delta px. So delta x is the uncertainty in position. Okay, uncertainty, delta represents uncertainty, means error. Okay, uncertainty in position, and delta px actually says the uncertainty in momentum. Okay, so it is greater than h upon 4 pi, greater than equal to h upon 4 pi, or if I write px as mvx, where delta vx is the uncertainty in velocity. So we will get this relation, delta x into delta vx is greater than equal to h upon 4 pi m. Now what does that mean, students? It means that If we are measuring, let's say, the position of the electron, that is the position of the electron with utmost accuracy, means the uncertainty in position is very less. If delta x is very less, then the value of delta vx would be greater, means the uncertainty in your velocity would be very high, and vice versa. If the delta vx is less, means the velocity is measured with accuracy, then the delta x would be more, means the uncertainty in position would be more. It means simultaneously we cannot determine, or we cannot tell the exact position and exact momentum with accuracy. Okay, there will be actually a blur picture. Okay, now if we cannot tell the exact position and exact velocity simultaneously, like, can you think of this thing that it rules out the existence of definite paths and trajectories of electrons? What Bohr said. What did Bohr said? Let's recall. He said that electrons revolve around the nucleus in definite paths, right? Definite paths, which he called as orbits. But according to Heisenberg uncertainty principle, what is happening? We cannot determine only the exact position and exact momentum of the electron. So how can we tell the exact path of the electron? We can just tell the probability, no? We cannot tell the definite path or trajectory the electron is following around the nucleus. What we can tell is that, yeah, electron might be in this area. Okay, in this particular area that I am shading. So electron might be present in this particular area. It is, we cannot tell its exact position according to Heisenberg's principle, right? So that's what we are saying now. For a subatomic object like an electron, it is not possible only to determine the position and velocity at any given instant. Okay? To an arbitrary degree of precision, mean with accuracy हम नहीं कर सकते. So it is not possible for us to talk about the trajectory or the path. Trajectory means path of the electron. Okay? And you know, this effect of Heisenberg uncertainty principle is only significant for microscopic objects, not for macroscopic. Let me tell you, let's say if I am having any macroscopic object, let's say whose mass is around about a milligram, means mass is 10 to the power minus 6 kg. Okay, that's macroscopic according to us. So if I found the value of delta V into delta X, so here it is coming out to be 10 to the power minus 28 meter square per second, right? Now what does that indicate, students? That indicates that the small value, now this 10 to the power minus 28 is an extremely small value, right? And these such small values are insignificant, no? Can you think of 10 to the power minus 28 having any significance around? No, now. So they are insignificant. That's why we are saying that if we are dealing with even a milligram sized object or more than that, then the uncertainties are having no significance. Okay. That's what we have seen by this example. But now let me tell you about electron. This is very important because that will lead to the development of the quantum mechanical model. So in case of a microscopic object, like I am having any your electron, let's say. So the value of delta V into delta X is coming out to be large. You see the mass of electron I have taken 9.11 into 10 to the power minus 31 kilograms. So the uncertainty is coming out to be around 10 to the power minus 4 meter square per second. Now this value is not that small that we can neglect, right? We cannot neglect it. Okay. Now let's say if I try to find out the exact location of an electron. Okay. So let's say if I am having the value of delta X as 10 to the power minus 8 meter, this is what we have got about the position of the electron with some uncertainty of this much. Okay. So the uncertainty in velocity would be, can you see, 10 to the power 4 meter per second. Yes. So you see here that if we are saying ki we know the position of the electron with a little bit uncertainty only, okay, with a lot of accuracy, so us time par the uncertainty in velocity is very, very large. Okay, so it is not holding good. So it means ki position and momentum of electrons we cannot tell simultaneously, so we cannot tell about the path also. That Bohr said कि electrons revolve in a definite path, but that is not holding true here. So that's what I said now, that we have to replace these by the statement of probability at a given position and momentum. Means हम ये बोल सकते हैं that at this given position and momentum, the electron can be found in this region. There's a probability that electron जो है वो हमें इस region में मिलेगा. Okay, so we cannot tell exactly कि electrons revolve in circular path. Okay, so this is what we are going to talk about in the quantum mechanical model of the atom, that is about the probability. So quantum mechanics, if I talk about quantum mechanics, it is the one which takes the dual nature, which talks about the dual nature of matter. Okay, it takes into consideration the dual nature of matter. So that's what is quantum mechanics. It's actually a theoretical science that deals with the study of motion of microscopic objects. And those microscopic objects की study वो कर रही है, and it is observing or it is holding true that they have wave-like and particle-like properties also. कि wave-like properties भी होंगी, particle-like properties भी होंगी. Then how the microscopic objects are behaving, if we are doing that study, that comes under the quantum mechanics. Okay, and even if you apply it to macroscopic objects, there is no difference. The results will be same as that from classical mechanics. Okay, so इसका मतलब this quantum mechanics is applicable for both microscopic and macroscopic objects, but it is more important to study in the case of microscopic objects. So now we have studied what is quantum mechanics and how did we reach here. Okay, so now we will not talk about the definite path of electron. हम बोल ही नहीं सकते according to Heisenberg's principle, right? So we will be now, from now onwards, we will be talking about the probability of finding the electron. So that is actually given by Schrödinger equation. So Schrödinger equation is actually a very important equation in terms of quantum mechanics that talks about the probability of finding the electron. Okay, so let us learn more about it. So students, the Schrödinger equation for any atom or a molecule having fixed energy, it can be given by H psi is equal to E psi. Now this H is actually an operator. It's actually a mathematical operator which we call as Hamiltonian operator. You will study more about it in physics also. So here we don't have to go in detail. So it's known as Hamiltonian operator. And when we solve this Schrödinger equation, this psi is actually a wave function. It is a wave function which tells us about the electrons. Okay. So when we are solving this equation for a hydrogen atom, let's say, we will get the values of E and psi. So E actually are the energy levels. So it tells us about the energy levels, all the energy levels the electron that can occupy, and phi is the wave function which has all the information about the electrons. Okay, they are categorized by 3 quantum numbers that we will study, N, L and M. Okay, so wave function actually tells us all about the electron, and the probability of finding the electron is given by psi square. So it actually tells us about the probability of finding the electron around the nucleus, ki in which area you are going to find the electron, or where is the maximum probability of finding the electron. Okay, so Schrödinger wave equation solutions give us the value of energy levels, and for each energy level the wave function has all the information about the electrons, and which are categorized by these quantum numbers. Okay, so if I talk about the important features of the quantum mechanical model, you can see, students, that it is actually a picture about the structure of the atom, from which we are getting from the Schrödinger equation. So the very first thing is the energy of electrons in the atom is quantized. Means, again we know quantized means can have only certain specific values. Alright, then the existence of quantized electronic energy levels is direct result of wave-like properties of the electron. So thus now we have discussed that electrons don't only show the particle-like but the wave-like properties also, and because of the wave-like properties we have these quantized energy levels. Okay. So we know that both the exact position and velocity of an electron cannot be determined simultaneously, and that is why the path of an electron in the atom can never be determined or known accurately. That's what I have been telling you now. We can only talk about the probability of finding the electron. We cannot talk about the exact path of the electron. Okay. An atomic orbital is the wave function psi for an electron. So this psi is known as the atomic orbital. Okay. So whenever I told you an electron is described by a wave function, we say that electron occupies that orbital, and that orbital tells us everything about that electron. Okay, so one electron orbital wave functions are there. All right, in each orbital, now please note that electron can have a fixed energy, and a particular orbital cannot have more than two electrons. And if I talk about multi-electron system, the electrons are filled in order of increasing energy that we will be studying later. Okay, so that is why for each electron, if you have a multi-electron system, there is an orbital wave function characteristic of the orbital it occupies. Means for each orbital, there will be a characteristic wave function. Okay, and all the information about the electron will be stored in its orbital wave function psi. Okay, and I told you that the probability of finding the electron is given by psi square, which is called as the probability density. So from the values of the psi square, we can easily find out the region around the nucleus where the electrons will be most probably found. Okay. So now students, we will be discussing about the quantum numbers and the orbitals. Okay. One by one we will be discussing all the quantum numbers. Again, this is a very important topic. All these were the conceptual things that we have discussed here regarding the quantum mechanical model. Now this is something very important that we are going to discuss that can be asked in your NEET exam as well. Okay. So students, since there are many orbitals possible for an atom, right? So each orbital will be having different shape, size, and that will tell us different things about finding the electrons. So if I talk about the quantum numbers, there are majorly four quantum numbers. The first one is principal quantum number, which is denoted by n. So this principal quantum number, it tells us mostly about the energy of the electron, right? And it tells us about the shell, means in which shell your electron will lie. So the value of n like corresponds to different shells, like if you have n 1 2 3 4 and so on, so the shell will be, first shell is k shell, then l, then m, then n, and so on. Okay, so this is about the principal quantum number, which tells us about the shell. Moreover, it will also tell us about the size of the orbital, because with the increase in the value of n, the size of the orbital also increases. Then if I talk about the second quantum number, which is your azimuthal quantum number, which is denoted by L. Now this L tells you about the shape of the orbital, like what will be the shape of orbital, and the value of L depends on n. Now for each value of n, the value of L goes from 0, 1, 2 up to n minus 1. Okay, and how, so each shell has a particular subshell also. So the number of subshells will be denoted by the value of n only. Like if I say कि n equal to 1 है अगर, तो उसके लिए जो L की value होगी वो that will be n minus 1 only, means 0 only. तो means सिर्फ एक subshell होगा उसमें. Okay, for the first shell. Similarly, n equal to 2 है तो L की value क्या हो जाएगी, 1 and 2. So there will be 2 subshells. Okay, and similarly so on. Okay, so they tell us about the shape of the orbital. Moreover, if I talk about the value of L, so if L is equal to 0, here I can write it. If the value of L is 0, 1, 2, 3, so on, so the subshells are S, P, D, F, G, H, and so on. For example, if I say I am having 1s orbital. Okay, so for here the value of n is equal to 1 and the value of azimuthal quantum number is 0. So can you tell me, like, if I have 3d orbital, so for here the value of n is equal to 3 and the value of azimuthal quantum number is 2. Like, okay, so because 2 corresponds to d. And these SPDF orbitals, they have different shapes that we will study. So this azimuthal quantum number tells us about the shape of the orbital. Now we have the magnetic quantum number, that is denoted by small m, which tells us about the orientation of the orbital in space. Okay. So students, the value of magnetic quantum number, that is m, will depend on L. So for each value of L, there will be 2L plus 1 magnetic quantum number. For example, if L equal to 0, so then the value of m will be equal to 2 into 0 plus 1, that is just one value. Okay, that is 0 only. Okay, like minus L se lekar plus L tak it will go. And let's say if L is equal to 2, okay, d orbital, like for p orbital, let's say L equal to 1, so m की कितनी values होंगी? There will be 3 values. Okay, that is -1, 0 and +1. Okay, similarly L equal to अगर 2 है, means for the d orbital, तो m की कितनी values हो जाएंगी? 2L plus 1 means 5 values. तो 5 orientation होंगी हमारे पास, that is -2, -1, 0, 1 and 2. ओके, तो क्लास यहाँ पर 5 तरह के हमें ऑर्बिटल्स मिलेंगे. जैसे p के केस में हमें मिलेगा px, py, pz, 3 are there ना. For d के लिए we will be get dxy, dyz, dzx, then dx square minus y square and then dz square. Okay, then the last one is the spin electron number, that is denoted by ms. So it will have only two values, either plus half or minus half. So it will tell you about the spin of an electron. So if the spin is clockwise, then we will say that the value is plus half. If the spin is anti-clockwise, we will say the value of ms is minus half. So it tells us about the spin of an electron. Okay. So students, I hope you understood about all the quantum numbers. So if I want to summarize, so you can note here that n defines the shell of the electron. It tells us the size of the orbital and the energy of the orbital to a large extent. Then there are n subshells in the nth shell, like L. L is the azimuthal quantum number which identifies the subshell and determines the shape of the orbital, and there are 2L plus 1 orbitals of each type in a subshell. Okay, like 1s orbital, there are 3p orbitals, 5d orbitals. Okay, and to some extent L also determines the energy of an orbital in a multi-electron system. Then ML, magnetic quantum number, it tells us the orientation of the orbitals. For a given value of L, we have 2L plus 1 ML values, okay, which is actually same as the number of orbitals present in a subshell. Okay, and ms is the spin quantum number, which refers to the orientation of the spin of electron. It can have two values, plus half or minus half. Okay, means either a clockwise or an anti-clockwise spin. And for any orbital, no, there can be a maximum of 2 electrons, and those 2 electrons cannot have the same spin. Okay, so they must have the opposite spins. That's we must know. Now that students, we have learnt about the orbitals, so we must know about the shapes of the orbitals also, like what are the shapes of the SPDF orbital. Now how we have determined the shape of the orbitals, let me tell you. So psi square tells you about the probability of finding the electron around the nucleus. Okay, so it is giving you the probability density of finding the electron at a point. Okay, so we can actually plot the graph between psi square and r. R is the distance from the nucleus. Okay, so when we plot these graphs, we can get an idea about the shape of the orbitals also. Okay, so what we are doing is we are just talking about the probability density of electron, ki what is the probability of finding the electron, and that will give you the shapes of the different orbitals. Okay, So here students, if we see, this is where we have plotted the psi, that is the wave function, and the psi square along with the radius, okay, that is in nanometer. So if you see here for 1s orbital, the probability is maximum near the nucleus and then it comes to 0. Now for 2s orbital, firstly it is maximum near the nucleus, it becomes 0. Then the probability density again increases and then again it becomes 0. So this area where the probability of finding the electron is 0, it is called the node. Okay, so for ns orbitals we will be having n minus 1 nodes. Like for 1s orbital we have 0 nodes, for 2s orbital we have 1, for 3s orbital there will be 2 areas of 0 probability density, means 2 nodes will be there. And simultaneously we can make the boundary surface diagram. So if we, these are the boundary surface diagrams. So if we draw these boundary surface diagrams, we can get an idea about the shape of the orbital. So each dot represents the probability of finding an electron at a particular instant. Now you can see for the s orbitals, like for 1s, 2s orbitals, the shape is spherical. So we can say that the shape of the s orbital is going to be spherical. So similarly, we can draw the shape of other orbitals. So here you can see students that the shape of s orbital is spherical. Now if I talk about p orbital, so we have three, px, py and pz for p subshell. So the shape is dumbbell shape. Okay, dumbbell shape you can see. So this is the area where the probability of finding the electron would be maximum. And for d orbitals we have double dumbbell shape. So here you can see this is dx square minus y square, dxy, xz, yz, and okay, so it would be your yz, okay, and then d z square. So these are the different shape of the orbital. So in s orbital there were radial nodes. Okay, now radial nodes means where the probability of finding the electron is 0. So for ns orbital we have n minus 1 radial nodes. Now in the case of p and d orbital, along with radial nodes there would be angular nodes. Now what are these angular nodes? So in the p and d orbital there will be a plane also that will be passing through the nucleus where the electron density would be 0, and that will be known as the angular node. So the total number of nodes would be given by n minus 1, like the sum of L angular nodes plus n minus L minus 1 radial nodes. So total number of nodes will be given by n minus 1. So this is how we have different types of orbitals, that is the shape of the orbitals. Okay. So now that students we know about the orbitals and the shape of orbitals, let's see how the atomic orbitals are filled. So to fill the atomic orbitals, we have basically three rules. The first one is the Aufbau's principle. Now these rules are very important for filling the atomic orbitals. So the Aufbau principle says that the electrons will occupy the orbitals having lower energy first, then before occupying the higher energy orbitals. Now how to identify the ones which is having lower energy? There is an n plus L rule. This is a shortcut that I am telling you. Okay, so students, the one having the lower value of n plus L will be having the lower energy. But let's say if two orbitals have same value of n plus n, so the one having the lower value of n will be having the lower energy. Okay, so this is the rule that you must keep in mind to find the energy. So now see, here it is written that energy is calculated by the sum of principal quantum number and azimuthal quantum number, means n plus L. So from n plus L rule you can find out which one will be having lower energy. Okay, so this is the correct order in which the electrons are filled: 1s, then 2s, 2p, 3s, 3p, and so on. Okay, so you can see here, this is actually a diagram. So you can draw this diagram and it will be easy for you to understand that how the orbitals are filled. Okay, like 1s, then 2s, then 2p, then 3s, then 3p, then 4s, and then after 4s 3d will be filled. Okay, because if you calculate the value of 4s, so it's 4 plus 0, which is 4, and for 3d you see 3 plus 2 which is 5. So clearly you can see that 4s will be having lower energy than 3d orbital. It is because of the shielding also, poor shielding effect also, but that we will be learning when we will be discussing these things in detail. Okay, so for as of now, just remember this n plus l rule, and whenever electrons are filled, they will be filled in this order only. So 4s filled before 3d, it will not be filled after 3d. Okay, so this is the flow chart that you have to remember. After that, we have Pauli's exclusion principle. So it states that maximum of 2 electrons, each having opposite spin, can fit in an orbital. Let's say if I am having a p orbital, okay, like p subshell. So there are 3 orbitals there, px, py, pz. So only 2 electrons can fill in one orbital, that too having opposite spin. I cannot fill 2 electrons like this or 2 electrons like this. Okay, this is wrong. So the correct way is that the spins must be opposite. So this actually states that no 2 electrons in the same atom can have the same values of all 4 quantum numbers. Okay, so like for here, let's say I am having this 2p orbital. All right, so for this 2p, these 2 electrons are there, the value of n is equal to 2. Okay, and it is 2p x, no, 2py and 2pz. All right, the value of L is 1. Okay, it's same. The value of ML is also same. Let's say it's -1, 0 and +1. So it's -1 because both of them are in the same orbital, 2px. Now the value of ms, the fourth quantum number, cannot be same. So it's plus half for one electron and minus half for other electron. So 3 quantum numbers can be same, but the fourth one cannot be same because the spin always have to be the opposite one. Okay, so that's why we are saying if the principal, azimuthal and magnetic quantum numbers are same, they must have opposite spins. Okay, means in the same orbital, opposite spin would be there. The last one is the Hund's rule. So Hund's rule says that it actually tells us the order in which the electrons are filled in a subshell. So it states that every orbital in a given subshell is singly occupied before a second electron is filled in an orbital. Means जब तक सभी orbitals में एक single electron नहीं आ जाएगा, the pairing will not start. Like here, let's say if we have 1s2, 2s2, then this is 2p, right? So the correct way of doing is, let's say I need to fill 3 electrons in this case. So I will be doing 1, 2, 3. Okay, I cannot do 1, 2 and then 3. So this is wrong. सभी में एक एक इलेक्ट्रॉन होना चाहिए. Now fourth electron अगर हमें fill करना है, so that will now the pairing will start. Okay, this is how the 5 electrons will be filled. So this is a wrong representation. If you have to fill 2p2, तो सब में एक एक electron होना चाहिए because these are degenerate orbitals. Degenerate means इनकी जो energy होती है, they will be same, like 2px, 2py, 2pz. इन सब की energy same होगी. So electron सभी में बराबर जाएगा. After that, the pairing will start. Okay, so these 3 rules, Aufbau's principle, Hund's rule and Pauli's exclusion principle, are important for filling up the electrons in the orbitals, and when we know this, we can easily write the electronic configurations also. Okay, so this is how, students, the electrons are filled, and that's what our quantum mechanical model is. Now let's say if I want to write the electronic configuration, so how I am going to write it. So like for hydrogen, we have only one electron. So it will start 1s, we need to write, and the number of electron is written in the superscript. Okay. Then helium. So both the electrons will go. So it's 1s, 2. Now 1s is completely filled. So for lithium, it will be 1s, 2, then 2s, 1. Okay, because 3 electrons. Then beryllium, 1s, 2, 2s, 2. Okay, separated by a comma. Then similarly 1s2, 2s2. Now this 2s2 is filled. So after 2s, which will be filled? Go to here. So here you will see 2p. Okay, not 3s, but 2p will be filled. So boron will be 2p1. Similarly carbon, 1s2, 2s2, 2p2. Okay, this is how. Then boron, carbon, then nitrogen, 1s2, 2s2, 2p3. Okay, so this 2p will be filled up to 6 electrons, because p subshell में you can have 6 electrons ना, 3 orbitals are there, so 2 2 2, 6 electrons जब तक fill होंगे we will be filling it, and after that like for nitrogen, then oxygen, then fluorine, okay, then neon. So 1s2, 2s2, 2p, 4, then it will be 2p5, and then 2p6. Now up 2p fill हो गया. Now we will be putting for sodium. So now sodium के लिए students we can write 1s2, 2s2, 2p6 and 3s1. Now you see कि 2p6 तक तो same as that of neon. तो जब भी noble gas आ जाएगी we can write it like this. So we can write the configuration neon 3s1. So neon से हमें पता चल गया that it is 1s2, 2s2, 2p6, क्योंकि इतना ज़्यादा हमें लिखने की ज़रूरत नहीं है, right? Okay. So this is how the electrons are going to be filled. All right. So similarly, like for argon, जब तक आप पहुंचोगे, it will be 1s2, then 2s2, 2p6, total 18 electrons होंगे ना, right? So 3s2 and 3p6. तो argon के बाद आता है आपका potassium. So potassium के लिए आप लिख सकते हो argon, then 4s1. Okay, like this. So this is how you are going to write the electronic configurations for the atoms. Okay, so class, with that we have completed this chapter, that is the structure of atom. If you are having any doubts in this chapter, if you are not able to understand any concept, please let me know in the comment box. Okay, so please watch all the 3 videos, understand the concept properly, and now the next task would be go through the NCRT. Okay, so whatever is given in NCRT, read it thoroughly line by line. Okay, read it and you will understand all the concepts, because the lecture that I have taken is also very closely related to NCRT. So we are focusing on NCRT only. Okay, and you can go to Memoneet tab, where you will find the questions on line by line NCRT. Means for every page you will find the questions. Okay, so you can have the elite plan of Memoneet app, and you can use all these features where you will find thousands of questions to practice, okay, that are based on NCRT. All right, students, so that's it from my side. Thank you so much. Take care. Bye bye.